Hello and welcome. Today we're going to be investigating the mobility equation, otherwise known as the Kutzbach criterion. Okay, so what does this do? Why do we use it? So this equation is used to determine the mobility of a 2D planar mechanism. Okay, so before we actually use this, let's try to understand it. So it can help us when investigating mechanisms. Okay. So let's go back to static for a second. So you guys should be familiar with these equations. So these are the statics equation of equilibrium for a 2D plane. So we have summation of fx equals 0, summation of m fy equals 0, and summation of m about the origin equals 0. So essentially what it's saying here is that the sum of forces in the x direction equals 0, sum of forces in the y direction equals 0, and the sum of the moments about the origin that you specified is equal to 0. Okay? So let's have like something like this, for example. Okay? Essentially, you're investigating 3 motions or 3 degrees of freedom that can exist in the 2D plane. Now, this will help us when we look at this mechanism. This equation. Okay? So this n right here represents the amount of links in the mechanism we're investigating. Okay? For example, let's say we have a mechanism that has 4 links, so n is equal to 4. This part pertains to this, so 3 times 4 minus 1, 3 times 3, 9, okay? So this first part will be 9, for example, okay? 9. What this means is that there's a possibility of 9 degrees of freedom if you summed up all the possible degrees of freedom that can exist in the mechanism. The reason why it's -1 is because one link in the mechanism has to be fixed for it to operate. Okay, so essentially it's saying that if you have 4 links in the mechanism, there's 9 possible degrees of freedom combined all together, and not necessarily there's 9 separate degrees of freedom, but there's 3 degrees of freedom, obviously the x, y, and the rotation. So among the links there's 9 if you add them all together that are possible. So theoretically in the mechanism there's 9 degrees of freedom that can exist. Okay, now this -2jl -2jh, they pertain to the constraints you minus from the lower order pair and higher order pair. So before we begin, let's just look at understanding the degrees of freedom. Okay, let's say we have a link, a rigid body, in the 2D plane. Okay, so let's be positive x, for example, let's be positive y. Okay, and we have a link. Okay, this link is capable of undergoing linear x motion, linear y motion, and rotational motion. So 3 degrees of freedom. Okay, that's where you get this 3 from in the beginning of the equation. So if we're looking at a mechanism, ignore this for now. Again, this 3n minus 1. Again, the -1 means you're minusing 1 because in a mechanism there's 1 link that's fixed. Okay, so let's say we had 4 again. 3 times 4 minus 1, 3 times 3, 9. So in a mechanism that has 4 links, you have a summation of 9 possible degrees of freedom that can exist. Okay, obviously this is theoretical and we have to consider this minusing part. Okay, now for example, let's say you're investigating a pin joint, okay, between 2 links. Okay, so this is 1 and 2. The pair that exists between those two, the rotational pair that exists between, so the degree of freedom pair that exists between these two is rotation. Okay, it's only 1 degree of freedom rotation. It cannot move left or right, so it cannot move right or left, and it cannot move up or down. Okay, the only motion it can undergo is rotational motion, so it's constrained in 2 directions. Okay, that's where you get this -2 from. You're minusing 2 for the fact that this part, remember this pin joint, if that exists, that's a lower order pair. The pair is low order. It has only 1 degree of freedom and 2 constraints. So I'm minusing 2 degrees of freedom. So this part right here gives you a theoretical summation of the possible degrees of freedom of the whole mechanism. Now you're minusing it to get an accurate answer, okay? So, okay, now you have minusing 2 constraints and low order pair. Because low order pairs only have 1 degree of freedom and you're minusing 2. So example, this is only rotational, so you have to disregard the x and the y. Now, this is minus 1. This one is minus 1 because it's high order pair. Some pairs can undergo 2 degrees of motion. For example, if you look at this link or rigid body on a plate, this can undergo the x motion and it can undergo the rotational motion. Okay, so this has 2 degrees of freedom. It's constrained only 1 degree. It cannot go in that direction. So it has 1 constraint. As for this, it cannot go like this x direction, nor the y. So it has 2 degrees. So this would be your lower order JL, and this would be your high order JH. Okay, this is, hopefully you understand now. When I do the example, you understand better. Okay, once again, theoretical possibility of minusing your constraint. Okay, so let's just do the equations. Okay, now for example, here you have a 4-bar mechanism. So you have 1, 2, 3, 4 links. So this I wrote 1 twice because it represents the ground. Okay, now let's just say, okay, I have 4 links. Okay, so n is equal to 4. Okay, n is equal to 4. Now these are all pin joints. Pin joints are all lower order pairs. Okay, so 2 to 1 is a pin joint. Okay, so low order. 3 to 2 is a pin joint. Again, pin joint. 4 to 3 is a pin joint, and 4 to 1 is a pin joint. Okay, there's 4 pin joints, so they're all lower order pairs. So JL is equal to 4, and there's no higher because there's only 4 pairs and they're all lower, so that means the higher order is 0. Okay, these all undergo rotational motion, so they're lower order because they only have 1 motion. They're constrained in 2 directions. Pin joints are constrained in the x and y motion, degree of freedom, and they only allow for rotational motion. So you can see the theta here to describe that motion that can exist. Okay. Oh my god, sorry. That's what there. Okay. So for determining mobility using our equation comes m is equal to 3. The possible degrees of freedom 4 minus 1 or n, minusing 1 because why? Because it's constrained. It's 1 length is fixed. Sorry. Minus the amount of constraints we have. So we have 4 pairs that are lower order, and each of those pairs are constrained in two degrees. Okay, 2 degrees of freedom. So it's minusing 2 4 times, right? Minus 0. So it becomes 3 times 3 minus 8. This becomes 9 minus 8 becomes 1. So this is correct because we know for a 4-bar mechanism, the mobility is 1. Okay. Now again, I have a mobility of 1 mechanism again, just slider crank mechanism. This undergoes rotational motion. This undergoes sliding motion. So our planar motion that we investigate is sliding, turning, and rotating. So sliding, turning, and rotation. So it's sliding, turning, and rolling. Sorry, rolling. Sliding, turning, and rolling. Okay. So again, you have 4 links here. So n is equal to 4. Now investigate the pairs. Okay, so they're all lower order pairs again. They're only allowed to move in 1 degree of freedom, and they're constrained in 2 degrees of freedom. Okay, so 2 to 1 is a pin joint. Okay, it only allows for rotational motion. 3 to 2 the same thing. 3 to 4 the same thing. 4 to 1 is sliding. Okay, only allows for that x motion. Okay, these are all low order. So again, 4. That means there's 4 pairs that are all low order. That means there's no high order, 0. So again, the same thing. The same numbers here. Again, the mobility would be 1 for this because you're doing 3 times 4 minus 1, which is 9 minus 2 times 4, which is 8. That becomes 9 minus 8, which is 1 again. So 1. Mobility is 1 here. Now, what does it actually mean? So, the mobility is an indication of the amount of inputs required to mobilize or give motion to the mechanism. So, in other words, you can think of it like how many motors you need so that when I apply it to the mechanism, it moves. How many inputs do I need to give the mechanism so that it moves? So, for example, these, let's say, are both crank induced. If I apply one DC motor, say a DC rotational motor right there that rotates, at these 2 points, that's enough to apply the mechanism. Assuming that the mechanism, that means that motor has enough power to supply the mechanism, it's enough, okay? Let's say mobility, for example, was 0. This means that it's fixed, it doesn't move. Essentially, it's a structure, okay? It's a structure. And the mobility was to be less than 0, a negative value. In terms of mechanisms, that means that there exists a redundant link. Or rather, the structure is preloaded. So there's something supporting the structure, helps support the structure. When developing structures, you want a mechanism below 0. Why? Because we want the structure to be ideal. We want it to be able to support loads. So that's it for today's video. I'll go over more difficult examples in the next one. Hopefully that helped. Take care, guys. Bye.